Greetings. And so our topic this week, acids and bases. And that's me, in case you don't know me yet, wearing my goggles, because I'm all ready to be safe in my kitchen. So, some greeting cards. You're as sweet as vinegar. And of course, we know vinegar is not sweet. Vinegar is sour. And that is actually the word sour in Greek is acidus. And so acids are sour. And anytime something has a sour taste, it has an acid in it. And so tart. And that's why when we have citrus, that puckering from the lemon or the orange or the lime, we make lemonade. And sugar, although if you test sugar, it's going to be neutral. Oh, on our body, it's extremely acidifying. It's terrible for our body. But that's the next slideshow. So danger, acids do get a special warning sign in the lab storage area. The acids are stored in a special cabinet and they are labeled in a special way. And if you were in lab, there would be always this special danger comment I would make in the lab. Acids are extremely useful. We use them for etching glass. They use them for etching silicon chips for making our computers and our phones work and all our technology. And you've all heard of battery acids. And you've probably seen this if you've ever looked at the battery in your car, because that is from the acid. Acids are very useful because they're very reactive, because that proton that they become. And this is one of the warning signs. So not only do they eat away at metals, they do this to our hands. So if you get a strong acid on you, you're not going to politely say, oh, what should I do? You will immediately go to the sink and keep your hand or whatever body part got the acid on you. And yeah, acids corrode. They eat away at our teeth and Coca-Cola. All the sodas are extremely acidic. So that is somebody soaked a tooth that had come out in Coca-Cola. And of course, there is acid rain, which comes from pollution from the industrial. And the most acidic place in your body is your tummy. So stomach acid is hydrochloric acid, HCl. The pH of our stomach is very low. 2. Very low, very acidic, and it's needed to be acidic because that's where it unravels proteins. So it doesn't break down the proteins, but it unravels it so the enzymes can get in and do their thing. And so, of course, people talk about, oh, I have too much stomach acid. Actually, stomach acid's needed more than just for helping us to digest, because without it, you cannot digest your proteins. It's also needed to absorb calcium and vitamin B12. And so a lot of people take antacids, which are going to neutralize the acid in your stomach and not allow it to do what it needs to do. And this was just, I thought was really funny. All right. And this is industrialization. We have created, most people think about global warming, but also acid rain. And so I had a student many years ago wrote a story about acid rain. They called it the sad saga of SOx and NOx. So SO2s and SO3s, sulfur oxides come from coal, and nitrogen oxides, well, they come from the air, and every time there's lightning, but also from electricity. And so there is no such thing as clean coal. All coal has sulfur, and the burning of the coal makes sulfur oxides. And those sulfur oxides and nitrogen oxides end up in our atmosphere, combine with the water in the atmosphere to make sulfuric acid and nitric acid, which are very strong acids, and then they rain down. And that is a forest from acid rain. One of the other things it does is it changes the climate too and allows certain bugs to propagate. It changes the pH of the water in lakes, and it allows demineralization of the rocks, and the fish can't live because of all the minerals that end up in there. And then for us, anything that was made out of marble anything that was made out of calcium or magnesium carbonate, it eats away at that. And so the Taj Mahal is actually going to disappear in the next like 2 decades or less because of acid rain. And in Greece, all the ruins are getting ruined. And Paul Revere's tomb, you can no longer read it because it was a marble, I believe. And so when I was a little gal, I actually saw Paul Revere's tomb, and you could see it, and that was just the cat going, "Egad, what are we doing? We can stop it, and we can change." So I googled what is a base or alkali. So another word for base is alkali, as we've talked about. And what Google tells you is it neutralizes or effervesces, which means it makes a gas. With acids, it turns litmus blue and is usually caustic. So caustic means it's going to burn you and me. It's going to eat away at metal. So just the same things we talked about with acids, that it is corrosive. There are batteries. So alkali batteries have hydroxide. So sodium hydroxide, potassium hydroxide, lithium hydroxide, and it's extremely useful for cleaning. Baking soda is, when you test this in your kitchen, window cleaner, unless you use vinegar, most people, the window cleaner they use is going to be something that's a nitrogen base, and toilet bowl cleaner. And so anything that has a bitter taste. So soapy taste. So I usually ask my students, I probably asked you this, which of you know what soap tastes like? And some people will admit it. I won't know because you'll all be black boxes. But I did not have a foul mouth, so I never tasted what soap tasted like, and I was never curious to put a bar of soap in my mouth. But I do know what bitter tastes like, because I do enjoy the bitter taste of coffee and, of course, chocolate. So anything that's bitter is actually an alkaloid from nature, and that bitter taste is a warning, because that usually means it's a poison. In small amounts, poisons are actually very useful, some poisons. And so an alkaloid means it's a nitrogen-based compound from nature, from plants, and they are bases. So whenever we see nitrogen, the key, when we see nitrogen, we're going to think base. All right. Should hopefully. So there's a couple different definitions we have for acids and bases. This was our first gentleman, Spontaneous. He actually won a Nobel Prize, one of the first Nobel Prizes, but his definition was that acids donate hydrogens and bases donate hydroxides. This is a definition almost everybody knows and uses, and it makes a huge assumption that it is an aqueous solution. It is water-based. That is a very valid assumption, since the Earth is water-based, 75%, the great blue marble, right? And you and I, we are also 70 to 80% water. And so that's a very valid assumption. So if you see hydroxide, you're thinking base. The Arrhenius equation, by the way, we will see in our last lecture, but it's not something you need to know, but we'll talk about it. He won the Nobel Prize for a lot of things that he did. And he then had a lunar impact crater named after him. How cool is that? He also was one of the first, back around the turn of that previous century, back in 1900, I think before that, he actually wrote a paper about that the Earth was going to warm up because that was the industrial age was happening. And so predicted global warming, and they laughed at him and said, "You're wrong, Sponge. What do you know?" But of course, we know he was correct. And so this is a chemist definition that we use, that you will have heard me use or will hear me. So acids donate protons. And so there's Bronsted and Laurie. And so acids donate protons and bases accept protons. So similar to our oxidation reduction reactions, but in this case, we're talking about protons. Excuse me. All right, and then there's Gilbert Lewis of Lewis Structures. And of course, those structures, these are some of his notes of his original pictures. Look a little different from what we were drawing with the dots and stuff. But he started thinking in this three-dimensionality. And so he looks at everything as far as electrons. It was all about the electrons for him. And so acids, he said, were electron pair acceptors. This is the flip of the protons. And bases are electron pair donors. And it's like, oh my gosh, which definition is it? Well, they're all the same. If you see nitrogen, it's a base. So this is an example of what Lewis was talking about. So a Lewis base, nitrogen always has that lone electron pair there. And that means that it is donating. It doesn't give it up fully. It's just making it into this special type of bond. Boron is an exception to the octet rule because of where it is on the periodic table. Everything's an exception to the octet rule. The octet rule is all about carbon, nitrogen, and oxygen because they do follow it. And you and I are carbon, nitrogen, oxygen based. All right. There's the chemistry cat. You guys can understand all these wonderful jokes even more now because we're talking about acids and bases. So what did the strong acid say to the weak acid? Hi. How's it going? Because hi is one of the strong acids. And so we will make a list in class. The thing that we need to know, the difference between a strong, most acids are weak acids. The strong acids are called strong because they completely donate all their hydrogens. They completely dissociate. This is a really nice slide because it uses the word dissociate. And weak acids only partially dissociate. So they don't fully give up everything. You don't get as many protons in the solution. And so you're not going to change the pH as much. The strong acid is going to have the lower pH. So more protons, more hydrogen ions, means a lower pH. So there we go, acids and bases. We usually think about it with that, with pH, that below 7 is an acid and above 7 is a base. This is what you're going to be doing in your lab, in your kitchen, is testing different things in your kitchen, in your bathroom, in your house, in your garage, and seeing if a test is an acid or base. And this is the gentleman, and this actually blew me away because I taught about acids and bases. I'd known about acids and bases. And the concept of pH itself is only about 111 years old. So Soren Sorensen introduced this concept of pH. Don't say. So pH, lower P, capital H. And it's just a way, it's a negative log of hydrogen ion concentration. So we will be doing the math with this. And it's the log scale. So every 1 point change is actually a 10-fold change. So a change from lemons to bananas, which looks like only 3 points, that's 10 times 10 times 10, or 1,000 times. So lemons are 1,000 times more acidic than bananas. So the other famous log scale is the earthquake scale. And so the difference between an earthquake of 2, which we have here all the time and aren't aware of, and a 5, where we would definitely be jiggling and wiggling and be saying, oh, this is not a good thing. All right, so actually I want to go back. This is a negative logarithm. So as you go lower, you become more acidic. And so stomach acid, they have it here as 1. And also as you go higher, you become more basic. So oven cleaner, bleach are going to be the things that test extremely, and actually Drano are going to be the things that are going to test really highly basic. All right, depending what you have in your house. You can go and buy coloring pages and color all these famous chemists. And yeah, you color by pH. So what you're going to do is you're going to measure pH of a bunch of stuff in your house. So this is, I believe, our last kitchen chemistry for the term. So have fun with it. Now, I don't have a pH meter in my house, so we're going to make our own. And so there are all these different chemicals that change color with pH. And I don't have any of these in my house, but I have actually probably all of these. And so all of these natural pH indicators, these are things that change pH When you add them to different solutions, the color changes based on the pH. So the pH doesn't change the color of these indicators. We're going to use red cabbage. I think it's purple cabbage, but everybody calls it red cabbage. And so I'm going to go through it as if we're doing it with red cabbage, but I do say in the lab, if you don't have red cabbage and you don't want to go to the store to get red cabbage, they do have it in all the stores and it's wonderful. You could try one of the other ones, and this picture is in your lab. One of the original ones was lichen. So this is all over everything here because of how wet and damp and beautiful it is. You can even get a little gnome lichen guy. So litmus paper, no licking the lichen. If you test an acid with litmus paper, it turns red. It rhymes, acid, red, and that's going to be true actually with our purple cabbage juice. So the purple cabbage litmus, if this is an acid, it turns it pink or red, and if it's a base, it turns blue. So base starts with a B, and so does blue. So in our lab, it does a similar thing with purple cabbage. The thing is with the bases, you get blues and greens and yellows. So you get a whole range of colors. The acids tend to have a limit, and that's why I think some of those other ones, let's go back. You can actually, might be really fun, like if you use tomatoes, you're not really going to notice, or curry powder, that acid range isn't going to work, but I was fascinated to think pure skin. It might depend. Radish, that you get an orange or a pink. In the base range, radish skin isn't really going to do much, but turnip, holy moly, look at the turnip. That's pretty awesome. That would be cool. All right, you can also carve your turnip. I think turnips were the first things that were carved for pumpkins instead of pumpkins. Hydrangea is also that flower, the blue flower. Some people, it will be blue, and some years it's white, and it depends on the pH of the soil. Our soil pH is very acidic here because of all the pine trees, and so we tend to have beautiful hydrangeas. So in lab, you're going to use, everybody calls it red cabbage, looks purple. To me, a lot of people don't like the taste of cabbage, but it is so good for you. So, SciSpy chemistry, full spectrum flatulence. This is from American Chemical Society. So there is a picture in your lab of the color scale. So you'll be able to compare when you test, say, Drano, and based on the color you get, you'll be able to estimate the pH. And this just shows you the molecule. And so every corner in these molecules are carbons. And those of you who will be with me in Chem 105, we get to do much more with it. All right, you got it? So you're going to chop up the cabbage. You're going to boil it for a few minutes. You're going to let it cool, strain it if you can, and then you use it as an indicator. It's really fun. It's really cool. It's fascinating, actually. All right, so try different cleaners in your household. You can try different things in your kitchen, in your bathroom. If you have soda, before you throw it out, because soda is very bad for you, you can check the pH of it. The problem with Coca-Cola is the dark color. It's hard to see the pH, so you do want things that are lighter. Yeah, if you use antacids, you'd smash them up, dissolve them a little bit, and then try them out. Pepto-Bismol, it's actually interesting, even though it's pink, if you have some in your home. And yeah, of course, Drano, different soaps, Gatorade, all sorts of stuff to test. Orange juice. You don't actually get orange. Milk, if you have milk in your home, different types of milk, all testing it. And then you can make a beautiful animal sculpture, sculpting with your cabbage. And then you're going to try and blend two of the colors and see what you get. And it won't be the same. If you mix red and yellow, you're not going to get orange. It's a post-lab question. And there are some bonus challenges. So one is if you can get the whole rainbow. And so put them in the order: red, orange, yellow, green, blue, indigo, violet. By the way, violet is neutral because that's the color of the cabbage juice. And so the water you're testing it with is neutral. So that's one of the bonus challenges. It's actually tough because the color orange is tough. Color yellow is tough for people. Another bonus challenge, actually this is part of the next lab, but is to try and make another dye. So if you have turnips at home, or you happen to be at the store and you pick up the red cabbage, pick up a turnip and try making a turnip dye. And I've never done it, and so that'd be really cool. And you are going to take pictures of yourself, but we should eat a rainbow every day. So here's me again talking to you about one of the big take-home messages from this term. The reason you have purple, whether it's purple cabbage or eggplant or artichokes or grapes, whatever you've got, it is this molecule. Let's all say it, anthocyanin. That's how I say it. It's from the Greek word that means flower, dark blue. So apparently that's not purple, it's dark blue. It's a pigment that makes anything you see that's purple, that's a food, and also the leaves that are outside that are the burgundy color, that are the reddish purple, that is anthocyanin in those leaves. So as the chlorophyll disappears, as the sun is disappearing, the other colors can come out, and so it was always there. So depending on the pH, it changes color. And these all have it. So apparently the really dark cherries and blueberries are not apparently blue, they're apparently purple, but they look blue to me. Some of the things it does, it makes you smarter, it slows down aging of your brain, and it makes you learn, as opposed to this crappy stuff, which makes your brain hyper. So no, 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 no. And that's the other lab that you're doing this week. So again, if you're still doing some of that other fake purples, egad. Yeah, and there was the beautiful molecule. It is great for your eyes. It is great for your immune system, something we should all be doing. It is great for anti-cancer. Yes, much more to love. That's pomegranates. Pomegranates are in season. Healthy liver. Yes, and cold and flu season is upon us. And can you eat too much? I don't think so. But if you feel bloated, anthocyanin apparently helps digestion. So remember safety in your kitchen. Johnny was a chemist. Johnny is no more. For what he thought was H2O was H2SO4. Attitude. Attitude is everything, and attire. If you're wearing flip-flops, unicorn slippers in your kitchen, well, I won't know. But you do have to take a picture of yourself doing this. So attitude is everything. So there's my twin brother, Joe, and he's got his goggles on as he's doing, look, we got the potassium chlorate demo to work that year. And yeah, you're never supposed to eat or drink or chew gum in lab. Well, in your kitchen, though, you should eat purple for a longer life. And so even though you only need like one leaf of that cabbage, don't throw it away. Make something delicious, part of the next lab, to eat the color purple, to eat all the colors. I actually like it raw. I put it in my salad with my greens, and I absolutely love it. I don't do the whole salad as it, but it's really crunchy. And whenever I'm a very messy cook, it falls on the floor. My dog eats it up. Yes, my dog loves cabbage, raw cabbage. I am not a fan of cooked cabbage, but I know many people love when I make cabbage soup. Everybody loves it. And don't leave a mess. Make sure you clean up in the kitchen, because I am not there. And if I was, I'd be making a bigger mess. So have fun. Blessings, blessings, blessings. You are all amazing. Have so much fun. I look forward to seeing your pictures. Bye-bye.